Okay, so day 3 of rational functions, but we're finally going to get to when the degree of the numerator is bigger than the degree of the denominator and there's no horizontal asymptote. What does that mean? So, recall what I just said. When the degree of the numerator is bigger than the degree of the denominator, we say there's no horizontal asymptote. However, in this situation, there's going to be an oblique asymptote. Oblique asymptotes are also called slant asymptotes. And here it says, if the degree of the numerator is bigger, exactly one more than the degree of the denominator, then there's going to be an oblique asymptote. A graph will never have both an oblique and a horizontal asymptote. It's only going to have one or the other. And then the function for the oblique asymptote is the quotient polynomial of q of x resulting from the division of a of x and b of x. So if you want to find the oblique asymptote, what you're going to do is you're going to do a of x divided by b of x using polynomial long division. You're going to get a function q of x. There might be a remainder, but you're going to disregard the remainder, and whatever you get for what you get for everything but the remainder is the function. Okay? So to find an oblique asymptote, we use long division and disregard the remainder. That's what it says right there. Okay, so let's get started on this one right here. And I'm going to tell you right now, not all of these are going to have an oblique asymptote. So we're just going to treat them as if they were a test question each time. Okay, so domain has to be done first always. You look and say, are there any restrictions? There's a denominator. Denominators cannot be 0. So x can't be -2. So now I'm going to say my domain is negative infinity to -2, union -2 to infinity. All right, now I'm going to look to see if there's any holes. If there's any holes, then I'm going to be able to cancel out common factors. So if I look at my numerator, I can only factor it to x times x, which I'm not going to do, and my denominator is not factorable. So there are going to be no common factors that cancel out. Therefore, there are no holes. Vertical asymptote, set the denominator equal to 0 and solve. If I set x plus 2 equal to 0, I get x equals -2. Next, is there a horizontal or oblique asymptote? So this is how to look on your test. It's not going to say horizontal asymptote. It's going to say horizontal or oblique, and you have to decide which one it is and then find it. So what we're going to do is we're going to compare the degrees. The degree in the numerator is bigger. Okay? It's 2 versus 1. So that means that numerator means there's no horizontal asymptote. Therefore, there's an oblique asymptote. So instead of writing the word oblique, I just circle the word oblique. And now I'm going to find the oblique asymptote. What you're going to use is you're going to use polynomial long division. You're going to do this divided by this. Okay? All right, so let's do that. X squared. X squared. And then remember, I want placeholders. So plus 0x plus 0 divided by, and that was x plus 2. And I'm just going to move this over because I feel like it. All right, so remember, you're asking yourself, what do I multiply this by to get this? That's x. I'm going to put it above my 0x because they have the same exponent. Distribute my x to the x plus 2. X times x is x squared. X times 2 is 2x. And now I'm going to subtract this off of my polynomial. I don't like subtraction. I'm going to change it to addition, so I'm going to distribute the negative. These cancel, bring everything down. So I have -2x plus 0. Start over. What do I multiply x by to get a -2x? That's -2. Distribute. -2x minus 4. Subtract that off. I like to add the opposite. This is gone, and my remainder is 4. Remember what it said right here in this last bullet point. To find an oblique asymptote, we use long division and disregard the remainder. So you're going to disregard this. You're not going to even use it. It has nothing to do with it. Okay. All right, your oblique asymptote is always going to be a line. So we're going to put y equals, and then it's whatever you got when you divided it, disregarding the remainder. So y equals x minus 2. Make sure that you don't just put x minus 2. It's a line. So you need y equals x minus 2. X-intercept, we set y equal to 0 and solve. It's g of x equal to 0 and solve. Remember, this is a fraction equal to 0, so the shortcut is just set the numerator equal to 0. I get x equals 0, so my x-intercept is 0, 0. My y-intercept, I'm going to plug in 0 for x and see what I get for y. In my numerator, I get 0, and my denominator, I get 2. 0 divided by 2 is 0, so my y-intercept is also 0, 0. We'll save end behavior for last. I can start it if I want. Limit as x approaches negative infinity of my function g of x is. Limit as x approaches infinity of my function g of x is. Now, if there was a horizontal asymptote, I could say it follows the horizontal asymptote. There isn't. There's an oblique asymptote, and it follows the oblique asymptote. But I don't know which direction it's pointing, so I have to graph it to figure it out. So we're going to start the same way. We are going to graph our vertical asymptote. There is no horizontal asymptote. We're going to graph our oblique asymptote, and then we'll graph any holes, which there aren't any, and our x and y intercepts. So my vertical asymptote is x equals negative 2. I'll start with that. Remember, asymptotes have to be dashed. All right, now I'm going to graph my oblique asymptote, which is the line y equals 1x minus 2. It's in the form y equals mx plus b, where b is my y-intercept of 0, negative 2, and then the slope is 1. So I like to make every single point on the line, but like very lightly, so that I can actually draw the line accurately. And then I'm going to go through and put my dashed line going through that. And there's my oblique asymptote. If there were any holes, I'd graph them next. There aren't any. And so now I'm going to move on to points that I do know. I know the x and y-intercept is 0, 0. So I have that point. Okay, so now I'm ready to graph. So remember, I need points to the left and to the right of the vertical asymptote in order to graph this, because I need to know where my two hyperbolic branches are. So do I have any points to the left of my vertical asymptote? No, I do not. So I'm going to make a table of values, and I'm going to plug in an x value to the left of my vertical asymptote. To the left of my vertical asymptote, I'm going to plug in negative 3. All right, so now I'm going to plug in negative 3. Negative 3 squared is 9. Negative 3 plus 2 is negative 1. 9 divided by negative 1 is negative 9. So now I know the point negative 3, negative 9 is on my graph. Right there. I could get more points. I can plug in negative 4 or negative 5, but 1's enough. I know that I have to follow my asymptote this way, and then this is going to have to bounce back around and follow my asymptote that way. To the right, I already have a point, and that's enough. I know I have to follow my asymptote, and there's what your graph looks like. All right, the only thing we haven't done is end behavior. So as you look left, what's happening to your y value? So as your x values get smaller, what's happening to your y values? That's an arrow pointing down. So that's negative infinity. As your x values get bigger, so as you look to the right, what's happening? That's an arrow pointing up. So this is positive infinity. And that's the gist of oblique asymptotes. So really we're just adding one extra piece of information to what we've been doing already. So it's a practice day plus a little bit more of information. All right, let's try another one here. It says for the function g of x, find. First off, we always have to find the domain first. There's a denominator, and I'm going to say the denominator, x squared minus x minus 2, cannot be 0. It's so incredibly important that you factor correctly here. If you factor wrong, you might miss out on a hole. Okay? So I need two numbers that multiply to give me negative 2 and add to give me negative 1. That's x minus 2 times x plus 1. Can't be 0. So x can't be 2 and x can't be negative 1. Now I'm going to write that as my domain. So I have negative infinity to negative 1 union, and then I have all values in between negative 1 and 2 union, and then anything greater than 2. All right, now I'm going to check in for any holes. Remember, in order for there to be holes, I have to cancel any common factors. This is not factored yet. The denominator I factored, but my numerator I haven't factored yet. So let's go ahead and do that. I have g of x equals, all right, my denominator I'm going to write down, which was x minus 2 times x plus 1. And now I need to factor my numerator. So if you look, people will always look at it and be like, and they'll make that noise, okay? Remember, if you're ever making the noise, look for a GCF, okay? Look for a GCF. There is a GCF of x squared, and I can factor that out, and then I have x plus 1. All right, so are there any holes? Sometimes the answer is no, okay? If I would have factored the denominator wrong and put plus 2 and minus 1, I'd be like, no. And then I'm going to have a lot of trouble after that, right? There is a hole here at negative 1 comma something. So I'm going to do negative 1 comma something. Now remember, I have a new function. I'm going to write it down over here. G of x equals x squared over x minus 2. I'm going to put my big giant cloud around it because that's what I'm using from now on. So from now on, I'm using this. Okay. All right, so to find the y value of the whole, I need to plug in the x value. So I'm going to do negative 1 squared in my numerator. And then my denominator is negative 1. I don't need a parentheses there. Negative 1 minus 2. So that is 1 over negative 3, or negative 1/3. And that's where the hole is. All right, now I'm going to find any vertical asymptotes. Remember, you're not looking at the original anymore. You're looking at the one in the cloud, okay? So vertical asymptotes at the denominator equal to 0 and solve, x equals 2. So another thing that I want you to notice is that you're not going to say you have one at x equals negative 1 and x equals negative 2. The reason that your domain has no values of the x value negative 1 is because of the hole, and at 2 because of the vertical asymptote. All right, horizontal or oblique asymptotes. Compare the degrees. The degree in the numerator is bigger, so there's no horizontal asymptote. That means there's no oblique asymptote. We're going to use polynomial long division to find the oblique asymptote. All right, what do I multiply x by to get an x squared? X. Distribute your x. X times x is x squared. X times negative 2 is negative 2x. Subtract that off of your polynomial. I don't like subtraction. I change it to add the opposite, so 2x plus 0. What do I need to multiply x by to get a 2x? That's 2. Distribute. 2x minus 4. Subtract that off of your polynomial. Gone. 4. That's the remainder. You can go ahead and disregard that. You don't have to write disregard every single time, but I'm just writing it down as I go. Okay, so now I can say, all right, I have an oblique asymptote. It's always y equals for oblique or horizontal asymptote because it's either a horizontal line or a slanted line. Y equals x plus 2. And I got the x plus 2 from right here. X-intercept, set your numerator equal to 0 and solve. I'm setting x squared because I'm looking at this numerator. I'm not looking at the original. Set x squared equal to 0 and solve. I get x equals 0. So my x-intercept is 0, 0. Y-intercept, plug in 0 for x and see what you get for y. I get 0 over negative 2, which is 0. I'll do my end behavior last, okay? All right, so I'm going to start by graphing my vertical asymptote at x equals 2. I'm then going to graph my horizontal asymptote at y equals x plus 2, so y-intercept of 2, slope of 1. Notice I'm really working on making that accurate, okay? All right, any holes? There is a hole at negative 1, negative 1/3. So left 1, down about 1/3, so I'm going to say it's right about there. And now I'm going to switch to blue, once again, personal preference. And I'm going to graph any other points I know. I know the x-intercept and y-intercept are 0, 0. Okay, so if I look at this, I say, do I have any points to the left of the vertical asymptote? I do, so I have enough information to graph there. That follows there. Now watch how I do this. I'm going to go like that, and then I'm going to skip over the hole, keep going, and that's how that looks. All right, do you have any points to the right of the vertical asymptote? The answer to that is no, so I'm going to make a table of values. X, Y. Plug in 2, right? Oh, no, I don't want to plug in 2. That's my vertical asymptote. I'll plug in 3. 3 squared is 9. 3 minus 2 is 1, so I get 9. So I have the point 3, 9. And now I can make this branch. Okay. All right, end behavior. So I'm going to do the limit as x approaches negative infinity of our function, which was g of x, is equal to, so as I look left, my y values are getting smaller, so negative infinity. Limit as x approaches infinity of g of x. As I look right, or as my x values get bigger, don't look at this one right here, because that's not where your x values are getting bigger. They're getting bigger as you look this way. They're going up. I'm going to get those marks off there, so that's positive infinity. And that's it. Okay? So the rest is all mixed practice. There's 3 of them, and I don't have you graph them because most people don't have the issues with actually putting it on graph paper. Okay? So we'll go through these just to make sure you're okay. And then if you have questions, you can ask in class. All right, domain, I'm going to say the denominator can't be 0. So I'm going to say x cubed plus 3x, x cubed plus 3x can't be 0. I'm going to factor this. I have a GCF of x. Then I have x squared plus 3 can't be 0. So x can't be 0. And then x squared plus 3 can't be 0. So that's x squared can't be negative 3. Square root plus or minus, I'm about to take the square root of a negative number, so this does not give me any more restrictions. My only restriction is x can't be 0. Negative infinity to 0, union 0 to infinity. All right, I'm going to check for wholes. So my denominator factors to x times x squared plus 3. And then I look at my numerator. My numerator does not factor. So well, that was a little out of control. So since it does not factor, that means that no common factors are canceling out too, since there's nothing that would factor out. So there are no holes, none. All right, vertical asymptote, set the denominator equal to 0 and solve. We already did that right here. Okay, and we got this and then this, which is out. So there's a vertical asymptote at x equals 0. Horizontal or oblique asymptote. The degree in the numerator is bigger, so there's no horizontal asymptote. That means there's an oblique asymptote. So off to the side, we're going to do polynomial long division. We're going to do 3x to the 4th, plus there's 0x cubes, there's 0x squareds, there's 0 x's, and then plus 4, divided by x cubed plus 3x. All right, what do I need to multiply an x cubed by to get a 3x to the 4th? That's 3x. Distribute. 3x times 3x cubed is 3x to the 4th. 3x times 3x is 9x squared. So make sure you put that under your x squared. Subtract that off your polynomial. I don't like subtraction, so I'm going to change it to add the opposite. These are gone. There's nothing here. I can bring this down. That's negative 9x squared plus 0x plus 4. All right, what do I multiply an x cubed by to get a negative 9x squared? And it's nothing, and it's because if you think about it, there's a 0x cubed here, and that's like asking what do I multiply x cubed by to get a 0x cubed, and the answer is 0, right? So there is no number right here. This is my remainder, right? And remember, I get to disregard my remainder. So my oblique asymptote is y equals 3x. X-intercept, set the numerator equal to 0 and solve. I'll do that off to the right here. 3x squared plus 4 equals 0. 3x squared equals negative 4. Divide by 3. X squared equals negative 4/3. Square root plus or minus. I'm about to take the square root of a negative number, so there are no horizontal asymptotes. Y-intercept, plug in 0 for x and see what you get for y. So in my numerator, I get 4. In my denominator, I get 0. 4 divided by 0 is undefined, so that means that there are no y-intercepts either. Okay? All right. Notice I didn't ask you for end behavior because I didn't have you graph it. And when there's an oblique asymptote, you need the graph, or I should say we need the graph to look at the end behavior. Okay, next one. Domain. So I'm going to say, okay, denominator can't be 0. So I'm going to say x squared plus 5x plus 6 can't be 0. So remember, being able to factor this correctly, super important. I need two numbers that multiply to give me 6 and add to give me 5, which are 3 and 2. So people will accidentally say 6 and 1. So x can't be negative 3 and x can't be negative 2. So my domain is negative infinity to negative 3, union, negative 3 to 2, union, 2 to infinity. All right, are there any holes? I already know my denominator factors to x plus 3 times x plus 2, and my numerator is factorable. There is a GCF. So I'm going to go ahead and factor this to see if there's any common factors. So my denominator was already x plus 3 times x plus 2. My numerator has a GCF of 2, and then there's x plus 2 left. So I can see that there is a hole. The hole is at -2, comma, and then now I need to write down my new function, h of x equals 2 over x plus 3. I'm going to put my cloud around it so I look at it and know that I'm only using that for the rest of this entire problem. All right, I'm going to plug -2 into h of x, the new h of x. So that's 2 over -2 plus 3 is 1. So I get -2, 2. Vertical asymptotes, set the denominator equal to 0 and solve. I get x equals -3. Okay, once again, notice it's not both of these because this one is part of a whole. All right, horizontal or oblique asymptotes, compare the degrees. This time the degree in the denominator is bigger, so there's a horizontal asymptote at y equals 0. X-intercept, set your numerator equal to 0 and solve for x. There is no x, so there is no x-intercept. Y-intercept, plug in 0 for x and see what you get for y. So if I plug in 0 for x, I get 2 still in numerator and then 3 in the denominator, so 0 2/3. Notice I asked you for end behavior here because there's a horizontal asymptote and you don't need to graph it in order to find the end behavior. Copy, paste, copy, paste, move over, get rid of the negative. Might be faster to write it, who knows? Okay, so it's going to follow my horizontal asymptote. So my horizontal asymptote's at 0, so that's going to be my end behavior. All right, last one for practice here, domain. The denominator can't be 0, so x squared minus 9 can't be 0. That means x squared can't be 9. Square root to solve, don't forget plus or minus. So x cannot be positive or -3. So my domain is -infinity to -3 union, -3 to 3 union, 3 to infinity. All right, so now I want to know if there are any holes. Okay, so my denominator factors to x plus 3 times x minus 3. My numerator is factorable. It is a difference of cubes, and we did do difference of cubes in our review, our algebra review quiz. But the good news is that you're going to see that what it factors to, there are no common factors that cancel out. Okay? So, we're going to say that there are no holes because there aren't any. There's no common factors. It's going to actually factor to, I can do it in my head, x minus 1 times, and then x squared, copy the sign, or sorry, I'm thinking of SOPs in my head. So square the first, that's x squared. Opposite, so it's plus, multiply, that's x, and then square the last plus 1. So there's not going to be an x plus 3 or an x minus 3 there. All right, vertical asymptotes, set the denominator equal to 0 and solve. So I get x equals positive and -3. Compare the degrees. The degree in the numerator is bigger, so there's no horizontal asymptote. That means there's an oblique asymptote. We're going to do x cubed plus 0x squared plus 0x minus 1 divided by x squared minus 9. I'm going to ask myself, what do I multiply x squared by to get an x cubed? That's x. I'm going to distribute. That's x cubed minus 9x. Subtract that off. All right, so I have no x squareds. I have -9x minus 1. What do I multiply an x squared by to get a -9? And I can't get anything, and that's because, remember, once again, this is a 0x squared, and this is plus 0, right? So we don't need it. We don't need the remainder. This is the remainder. So this is y equals, and then what I got up here, which is x. X-intercept, set your numerator equal to 0 and solve. You can solve it by factoring, or you can add 1 to both sides and cube root to get your real 0. So if I do that, the cube root of 1 is 1. So I have the x-intercept of 1, 0. You'd be missing your imaginary zeros, but we don't need those. Y-intercept, plug in 0 for x and see what you get for y. I get -1 over -9, which is positive 1/9. Okay, that's it for today.